Hello, everyone. Welcome to pre-lecture 12. We're going to be talking about some equilibrium today with Le Chatelier's principle. So Le Chatelier's principle, we talked about a little bit in class last time, but just as a reminder, Chatelier's principle describes what happens in an equilibrium system when a stress is put upon it. So say we are at equilibrium when Q equals K, we add a stress to the system. That could be adding more reactant or more product. It could also be changing temperature or pressure. What Le Chatelier's principle tells us is that the system will respond in that it will respond to that stress to reestablish that equilibrium. Okay. And so in class, we talked about the kinetic interpretation, where we think of this of maybe we add more reactant, and we know if we add more reactant, that will increase the rate of our reaction according to our rate laws. The same would be true if we added more product, it would increase the rate of the reverse reaction, thus forming more reactant, right? Yeah, so that's the kinetic interpretation. Something I would recommend is maybe considering the reaction quotient interpretation in most situations. I just think most students tend to picture this a little bit easier. So where we have our reactants over our products raised to some power. And so as our denominator grows larger, we'll have to form more product in order to reestablish equilibrium. And so I know we've already had some practice with this, thinking about if we have more reactant or more product, which way reaction will move. That's something that must be true, okay? And so in this example, we could add more H2 gas, for example, and if we added an excess of that, we could form all of our product. This is one of the ways you can drive a reaction in equilibrium towards products to get 100% yield, even if it's not a super favorable reaction, okay? So that is the reaction quotient interpretation of Le Chatelier's principle. And just a reminder that, of course, as QC is greater than KC, the reaction will shift left, whereas if Q is less than K, the reaction will move to produce more products, right? Okay, so that was what we talked about in class. We can also talk about Le Chatelier's principle in terms of pressure. And so this is essentially a rearranged version of PV equals nRT, which hopefully you remember from the first semester of Gen Chem 1. Okay, and so if we consider this reaction where we have a Kp value, where we have 2NO2 being in equilibrium with 2NO and O2, we would put our products over our reactants as usual, raised to their powers. But what if we changed the volume of our container and say we made it 3 times smaller, then the partial pressure of all of our species would triple. And so in order to do that, we would need to add 3s in front of all of our partial pressures, and then we could calculate the effect on Q, which would tell us if our reaction will move, of course, towards products or reactants. And so if we square things, essentially, then these 3s turn into 9. Those come from the squared property right there. If we multiply our top, 3 times 9 is 27. And then if we reduce our terms, it would mean that basically if we take 27 divided by 9 out, we know that if we reduce our volume of our container by 3 times, that means QP is going to be 3 times greater than KP. So if Q is greater than K, that of course means that we need to shift towards reactants, forming more reactants in order to reestablish our equilibrium, right? Okay. So we can also talk about our Le Chatelier's principle in terms of temperature. Really every equilibrium constant is temperature dependent. And so this will relate back to the ratio between our forward and reverse reaction, and ultimately the Arrhenius equation, right? But it's often easier to think about this in terms of enthalpy. So that is our delta H term. And so if we have an exothermic product, we're going to be releasing heat. And it's easiest to consider heat a product in those sorts of reactions. Then the opposite is true for endothermic reactions, where if we have to put heat in order to get a reaction to go, that can be considered a reactant, right? And so here we have a reaction. We have decomposition of N2O4 forming 2NO2. It is an endothermic reaction, right? Because our delta H is positive, and so we would consider heat a reactant there. And so if we raise the temperature, that would be the same thing as essentially adding more reactant. And this will shift our equilibrium towards the right, meaning that we'll get the formation of more of our product, okay? If this was instead an exothermic reaction, heat would instead be a product, and so adding more heat would drive the reaction to the left, forming more reactant to reestablish equilibrium, right? Okay, we've also talked about catalysts in chapter 12, and so a reminder that a catalyst will lower the activation energy of a reaction, and so this is essentially just a review of that, but it is also to say that both the forward and reverse reaction rates will occur faster, but that means that our equilibrium will be established faster, but the key point here is that the distribution of products and reactants will not change. And so a catalyst is very important for having a lot of reactions go fast, but again, it will not affect the final concentrations at equilibrium of our reactants or products, okay? One cool kind of application of this that I like to talk about is called the Haber-Bosch process. And so this is where you use N2 gas and H2 gas to produce ammonia, NH3. And ammonia is what makes up fertilizer for the most part. So you can react ammonia with nitric acid to make ammonium nitrate. That's most of what we put on fields in order to fertilize it, okay? So annually, this is about 1% of the energy in the world goes to produce this. And without the Haber-Bosch process, we wouldn't be able to grow enough food to feed about 3.5 billion people. So roughly half the population of the Earth. So incredibly important process. Here's another sort of graphic from it. So basically, if we were not able to make this synthetic fertilizer, we would only be able to get to about 3.5 billion people. But as you can see, the blue line is our actual world population. So just one of the ways in which chemistry is really sustaining modern life. The Haber-Bosch process, though, the reaction that occurs where we have N2 and H2 reacting to form NH3 actually has a pretty small K value. So 1.0-ish times 10 to the negative fifth. But this process is run at high pressure of gases and high temperatures, and also uses a catalyst, I believe iron oxide catalyst. And the constant removal of NH3, which is one of our products, from the reaction chamber, so it's constantly removed, driving the reaction again towards our products. Okay, so again, this is the apparatus that is used to produce ammonia. I think it's super cool stuff, very impressive that we're able to do this. And yeah, I hope you enjoyed that too. One other thing, the person who developed, or one of the people who developed the Haber-Bosch process, as you may have guessed by the name, was Fritz Haber. And so he is one of these people that was awarded half the Nobel Prize for his work in 1918, which again related to the development of this production of ammonia because it literally feeds the world. However, he is also considered the father of chemical warfare because he invented most of the chemical weapons used during Trench Warfare in World War I. And so just kind of wanted to give you a little brief biography there. I think he personally looks a little more supervillainy to me than maybe a world hero, but kind of a very complex person that we try and deal with as chemists. Okay, so that is his great contributions and moral failings, I think, are again just a fascinating story. So that's where we'll leave it for today. We're going to do lots of practice problems in class, so come ready to learn. I hope that was informational, and I hope you have a good rest of your day. Let me know if you have any questions, and see you in class.